Why is it that when a piece of iron is dropped into water, it sinks to the bottom? But when a foam ball is thrown into water, it always pops to the surface no matter how hard you try to press it down. Does it really mean that the water is holding up the lighter objects? In the context of the energy filament theory, the answer is not that simple. Instead of the water lifting the object, the reality is that water is rearranging itself to find the most efficient tension distribution. The so-called buoyancy is, in fact, a side effect of high-tension water pushing lower-tension objects upwards, as it seeks the best possible distribution of energy within the system. To understand this better, imagine water as a collection of small, tightly packed blocks. Each of these blocks, being tightly compressed, works to support the underlying layers of water by bearing the tension created by gravity. Now, when you drop an object like foam, which has low density, into the water, it's like forcing a soft material with a much more flexible structure into the water. The tension inside the water is suddenly altered, and the system realizes that it would be more efficient to push the foam upwards, as this allows the denser water below to take on less tension. This process, the rearrangement of the system to achieve a more balanced state of tension, results in the foam being pushed upwards, a process we experience as buoyancy. In contrast, when you drop a piece of iron into the water, things work differently. The iron is already a dense, tightly packed structure, meaning it inherently exerts a higher downward force. When the iron is placed in the water, the surrounding water immediately feels the strain of this added weight. No matter how the water tries to adjust itself, keeping the iron near the surface would disturb the overall tension balance. So, the water effectively decides to allow the iron to sink further into the water, finding a deeper, more stable position where it can be surrounded by water layers that can better handle the density of the iron. In this way, the water is adjusting itself in response to the iron's weight, and the iron sinks as a result of this redistribution of tension throughout the water. Archimedes' principle, which states that the weight of the displaced water determines the buoyant force, can be understood in terms of the energy C as follows. When you place an object in the water, it effectively takes on the tension responsibilities of the surrounding water layers, especially the deeper layers. The amount of tension the object assumes determines how much force the water will use to push it upwards. This isn't an abstract concept. It's a fundamental aspect of how the energy C works to maintain balance. The concept of buoyancy is simply the result of this redistribution of tension, which helps create a system that is as efficient as possible. Now, consider the case of a hot air balloon. The process is very similar. Air, like water, is a tension field, but here gravity presses it downward, creating a density gradient. The air inside the balloon is lighter and requires less tension. The cooler, denser air outside the balloon naturally pushes it upwards in an effort to equalize the tension distribution across the whole system. This is exactly why a hot air balloon rises. The surrounding air, which is more tightly compressed, pushes the lighter air upward, creating an efficient flow of energy in the system. So, in both the case of the foam and the iron, the phenomenon of buoyancy is not about the fluid actively holding the object up. Instead, it's about the fluid trying to redistribute its internal tensions to achieve the most efficient state possible. When an object displaces the water or air, it is, in essence, pushing against the flow of tension in the system. As a result, it ends up in a place where the system can achieve its lowest possible energy state, thus creating the sensation of buoyancy. This perspective on buoyancy is different from traditional thinking. It doesn't view buoyancy as a force that simply exists or is pushed by the surrounding fluid. Instead, it's an effect of the fluid itself rearranging its internal structure to find the most balanced and energy-efficient configuration. It's all about finding the least painful path for the energy involved. So, when you observe buoyant objects floating in water or air, you are witnessing the results of a complex, energetic systems working to minimize overall tension, a constant search for balance within the energy C. Tap follow, share it on New Physics, Clear Universe.